Welcome to 9.2, part 2. We're going to be continuing on with that notion of and or in compound inequalities. Now, this right here is a compound inequality, and there's a couple different ways we can solve it. I'm going to solve it as a compound inequality, then I'm going to break it into the and pieces. So here, if we're trying to solve this, we're trying to get the x, so we just have a 1x in the middle here. So we need to get rid of this 5 like we normally would. And now, whatever we do to one piece, we have to do to each of the pieces. That is, whatever we do to the left side, we have to do to the right side, and we have to do the middle. So if we're taking 5 away from the middle, we'd have to take 5 away from the left and the right. So on the left, negative 10 minus 5 is negative 15, greater than or equal to. These cancel, so we have negative 3x, greater than or equal to negative 6. Then finally, we're going to divide the middle by negative 3. But in order to do that, we have to divide each of these sides by negative 3. And when we do the negative, we have to flip all of the signs, just like we would with a normal inequality. So flipping this around, greater than or equal to, this gives us 5. Cancellation here, we get x. And then we get, flip the sign again because we're doing the negative, and we get 2. Now, what we get here is this. 5 is less than or equal to x, which is less than or equal to 2. So really, this is not a great thing. And if we look at this, it doesn't make any sense. Like, are there any numbers that are bigger than 5 and less than 2 at the same time? Answer is no, and that's why we get the empty set. Okay? So another way we could think about this is an and. We could think about this first piece. We could have negative 10 is greater than or equal to negative 3x plus 5, and negative 3x plus 5 is greater than or equal to negative 1. So if we solve these individually, subtract 5, negative 15 is greater than or equal to negative 3x, divide by negative 3, and this gives us our 5 is less than or equal to x. So if we graph this, point at 5, greater than or equal to, we're going over to that side, so that's what it looked like. Now, looking at this piece right here, we also subtract 5. This gives us negative 3x is greater than or equal to negative 6. Divide by our negative 3, we get x is less than or equal to 2. Now, just graphing this piece, we'd have 2, and we're doing it down there. Okay? So, and this is an and problem. So, an and problem, we're looking for where the intersection pieces, where are these two graphs overlapping? Since they're not overlapping, there is no solution to this, so the solution is said to be the empty set. That is the set that contains no numbers. So that's what we have there. So we could solve this as a compound inequality by doing the same thing to every side like we have over here, or we could break this up into an and problem like we have here. Now, same thing on the second one. This is classically an and problem, but it's a compound inequality. So I'm going to solve it as a compound inequality. So I want to get this x here to be just a 1x. So I need to get rid of this 5 in the denominator first, multiply everything by 5. 5 times our negative 4, that's negative 20, less than or equal to. Because we're multiplying by a positive, we don't flip the signs. This 5 cancels with that 5, so we have 7 minus 3x is less than or equal to 20, or 5 minus 4 over there. Get rid of the 7, so subtract 7. So it gives us negative 27, is less than or equal to negative 3x, which is less than or equal to 13. Then once again, we're dividing everything by negative 3. So dividing by negative 3, we have to flip all of these signs. So do that right there. So negative 27 divided by negative 3 is 9. Flip the sign, greater than or equal to. We get our cancellation here, so we get our x. Flip the sign, and then we have our 13 divided by negative 3, negative 3/13. So I don't like the way this looks. I like it when the smallest number's on the left and the right. So we can actually rewrite this just as negative 13 thirds is less than or equal to x, which is less than or equal to 9. So we can graph this kind of in two pieces if we think about this. First piece we could have is this. We'd have x is greater than negative 3/13, greater than or equal to. So we want a solid dot, negative 13 thirds, shading to the right because x has to be greater than that. And then we could graph the second piece right here. X is less than or equal to 9, Put our 9 right there, less than or equal to, we're shading there. Because this is classically an AND problem, we're trying to find where the overlap is. The overlap here happens between negative 13/3 and 9. Because we're including both of these points, we use the square and brackets. So right here, this gives us both notations. Over here we have like a set builder notation. Over here we have the interval notation. And over here we have the graphic representation of what's going on with the solution set. Okie dokie. Now we're moving into some OR. Now OR, as opposed to the AND, we're not looking for the overlap on the graphs. We're saying anywhere that's colored by either piece of the graph is going to be part of our solution set. So let's just solve this. We're going to solve these individually. Subtract 3 from both sides. We get x is less than negative 5. Okay, so x is less than negative 5. Circle at negative 5. Less than means we're shading off to that way. Solving this one, subtract 3 from both sides. We get x is greater than negative 1. Circle once again because we have less than negative 1. X being greater than negative 1, we're shading off to the left. So, notice that our solution set is two distinctly different pieces. They call these two disjoint pieces. There's the piece over here, and there's the piece over here. So we define each of these differently. Now, this would be a perfectly good, with an OR in the middle, that would be a perfectly good set notation type solution. If we wanted the interval notation, first we talk about this interval. Well, the interval to the left is the interval from negative infinity to negative 5, not including negative 5, so we have the parenthesis. Then OR, we use that union symbol, so we could put a U there. Now, the second interval starts at negative 1 but doesn't include it, so we have our parenthesis and goes all the way to infinity. And once again, we're always reading this from left to right. So first we encounter this interval, that's what we have right here. Then we encounter this interval, that's what we have right there. So this is the interval notation. Up here, that'd be the set notation. And then we have the graph of the solution. So, keep going on with these ORs. Here, isolating the x, add 1. So we get 7 is greater than 2x, divided by 2. And we get 7 halves is greater than x. Now, 7 halves is greater than x. I like to write this as x is less than 7 halves. Saying the same thing, notice that we, with the pointing piece is sticking into the x, the biting piece is biting into 7 halves. It's just, when I read it like this, I think it makes more sense to students. So let's solve this next one. Add 1, add 1. So we have negative 3 is greater than, or less than or equal to 2x. Divide by 2. And we get negative 3 halves less than or equal to x, which I will write that with the x on the left as well. So we have x is greater than or equal to negative 3 halves. So graphing these pieces individually, go ahead and do this one in red. 7 halves. Right there, so we have the open circle at 7 halves. Because x is less than that, we're going to shade to the left. Graphing this one we'll do in blue, we have x is greater than negative 3 halves, so negative 3 halves. Shading to the right. Now, because this is an OR problem, we're looking for anywhere that is shaded by the graph. Well, the whole graph is shaded, so we could represent this in a couple different ways. As an interval, we could say goes from negative infinity to positive infinity, so any number makes this true. The other thing that we could say is all real numbers. That is, any number you can think of, you can put into either this or that, and it's going to make at least one of those true. And if it's a number between right here and right here, it's going to make both of those true. So, or once again, we just need to find something that makes either of these true or both of them true at the same time. So, all real numbers. And that's kind of a special case. Generally speaking, the OR problems kind of look more like this one right here, and the AND problems look more like this thing right here. That's kind of classically like AND is we're looking for the intersection, or we have the two tails that are going off, but that's just kind of generally, 98% of the time it looks like that. So we'll do this last one. Once again, we have an OR, so I'll just go ahead and draw a little line differentiating, and we're going to be graphing this. And once again, we're looking for any piece of the graph that's shaded by the line. So first thing here, we need to get rid of the 6. So multiply by 6, multiply by 6. 6 is canceled, so we get our 2x minus 5 is less than or equal to negative 18. Add 5. 2x is less than or equal to negative 13. Divide by 2, and we get x is less than or equal to negative 13 halves. So, circle negative 13 halves. We're shading to the, oops, and we want a closed circle because we have less than or equal to. So, that's looking good. So we have our negative 13 halves. X is less than that, so we're shading to the left here. Multiply both sides by 5. Cancellation, so we get our 2x minus 5 is greater than or equal to 20. Add 5. So we get 2x is greater than or equal to 25. Divide by 2, and we get x is greater than or equal to 25 halves. So, mark at 25 halves, solid. Shading this to the right. So it kind of looks like this classic OR problem. So if we put this or that would be a set builder notation. The interval notation for this, well, we have two distinct intervals. So this first one, we have negative infinity to negative 13 halves. And because we're including that, we use square and bracket. Union, square and bracket because we're including the point, 25 halves to infinity. So, interval notation, the graph, and then the set builder notation. So hopefully that made sense. This and OR stuff is going to really be important for what we talk about next, absolute value equations and inequalities. So make sure you really kind of understand this before we move on. All right, see you next time.